So the first thing we're going to talk about is how text is converted into a vector so that a neural network could work with it. Suppose we have an incompleted sentence, like chemistry is. Well, there are a couple ways you could finish the sentence. For example, you could say chemistry is fun, chemistry is difficult, chemistry is boring. All this work. But something like chemistry is salads doesn't make sense at all. So, now we want to develop a neural network that can predict the next few words in an incomplete sentence. So in the network we just created here, notice how there are only 3 rows or 3 layers in this neural network. Suppose we have an incomplete sentence like my New Year's. So we're going to pass this as the input for this neural network. And for a neural network that's trained really well, the outputs will be something realistic, like resolution, goals, dreams, etc. The output isn't a prediction, but rather it is a probability distribution of what word might occur next. And the most important part about this is the central layer. We consider how active each neuron in the central layer is and accordingly create a vector depending on their activation. And for a neural network that is good at predicting possible words in an incompleted sentence, the information encoded in the central layer must be useful. Note that in this example, the center layer only has 4 neurons, but usually it has around 300 or more neurons to encode this information. So for any sentence that we type, we can get the vector of the sentence by simply passing it to this neural network and getting the activations of the central layer. So now we want to combine this text vector alongside the image vector that we have. Suppose that after vectorizing the image, we have an arrow pointing in space like the following. Now suppose we have another vector for the following sentence that says a 3D digital art of a salad. Now both of these vectors mean the same thing. They both represent a 3D digital art of a salad, except one of them is in image form and the other one is in text form. When we combine the image and the vector together, we want them pointing in around the same space because they physically mean the same thing. So our goal is to change these two vectors so both of them point in around the same space. At least that is what we want. But in reality, this embedding of the text alongside the image happens by another neural network. For example, the clip neural network from OpenAI. So what's happening in this neural network is really a black box, but what we are trying to accomplish is similar to what I said earlier, which is trying to convert one of the units to the other. For the illustration I provided, I only gave a 3-dimensional example, but in reality, if you look at these vectors, they're super long, typically over 1,000 dimensions long, which is a little tricky to visualize. So a 3-dimensional variant is a good way to illustrate what's happening. So now we're going to talk about encoders and decoders. So let's pretend like the following vector is a vector of an image embedded with a text. So many times, as I showed earlier, the vectors we get are super ugly and super long. We don't want that because computers may take way too long trying to use it. So with encoders, what we try to do is simplify the vector so it's easier for the computer to use while also maintaining the same information. So in a loose sense, this basically means pushing the vector down into a lower dimension. This is what we call a latent space. The neural network in this latent space is working with data that is compressed, so it is easier for it to do computations. To illustrate how the latent space works, take an example of the latent space of a random neural network. Here we see all salads are grouped on the top right of this page, while the dog is grouped in the bottom left of this page, while other images are grouped in the top left of this page. So basically, what a latent space is it is a way for neural networks to understand the compressed data. The same way we humans can tell the image is a salad by looking at the vegetables, the neural network can tell this image is also a salad by looking at the types of numbers in the image vector. So, an encoder network basically puts an image into the latent space so the neural network could understand what's happening. For example, suppose you had this really good looking image on the left side, but when you pass it through the encoder network, what it does is it converts the image to a lower dimensional form, which in this case would mean making the image look much worse, like the one on the right side. But we do not want the final image to look bad either. That's where the decoder comes in. It takes any information from the latent space and converts it back to a version that we humans could understand. So instead of getting an image that looks terrible, we're actually gonna get a nicer looking image. Now, to look at the difference between the encoded image and the non-encoded image, we can see that the non-encoded image has 512 by 512 dimensions. Meanwhile, the encoded image is much smaller. So this is an important point to note. Everything from here on happens in the latent space, or with the compressed data that was created by the encoder, because that's what a neural network understands. Now suppose we have a noisy image. We want to create a network that can undo the noise, or in other words, predict all the noise in the image. As usual, we create a new neural network. And for the input of the neural network, we put in the noisy image. And for neural network that's trained really well, hopefully the output will be all noise in the noisy image. So now what we do is we take the noisy image and subtract the predicted noise from it. And hopefully when we do that, we get back our original image. Now for the fun part. Suppose you want to draw a 3D digital art of scientists in a library. We first start off with a random set of noisy image. Now, the actual noise we start off with doesn't really matter in this case. But the important part is that the text is embedded with this noisy image. So as we talked about earlier, the text has to be embedded with this image. And now we pass it to the neural network that can predict all noise in the image. Remember how the text is embedded with this image? Well, this neural network is now trained to undo noise depending on the text that is embedded with the image. So, if we had different text, the noise predicted by this neural network would be completely different, even though the actual image of the noise is the same. And remember, the actual image doesn't have the noise, but rather it's the image in the latent space that we're adding noise to. So now the neural network predicts all noise in this image. And what we do is we take the predicted noise and subtract it from the original noisy image. And initially we might get something that looks a little wonky. But then what we do is add back most of the noise, but not all of it, to this wonky image. And remember, we're not adding noise to the actual image, but rather we're adding noise in the latent space. So now with this noisy image, what we do is we once again pass it back to the neural network that can predict the noise in this image. And once the neural network predicts the noise, what we do is we subtract the predicted noise from the original image. And then hopefully this time around, the image looks a little better. And we repeat this process over and over again, usually 20 to 50 times. And by the end, you should be able to see an image that very closely resembles the prompt you typed in. Now this process might seem a little random. Just adding noise and undoing it somehow magically creates an image. But if you think about it, it's an extremely good strategy, because the neural network isn't perfect. So anytime you ask it to predict the noise in an image, it's not going to be 100% accurate. So in a sense, it's losing some image in the information and putting in something else. And now I want to finish off this video by showing this process in action.